action, perception, decision-making, interaction, and communication. Also, in all of them, there is learning and adaptation. But this is something that we will talk later on. But now let's see each one of these, what they mean. Well, first, action is once we have perceived our environment, we have make the decision what to do, move, stop, talk, and then we do the action itself. And this action itself means that the robot move and do something together with the human and in the environment. When we do with the human means implies interaction. When it tries to tell something to the person, it means communications. And anytime is perceiving the environment, and that is the different elements. Okay, first, let's go into a little more in detail, not too much detail, but a little more. Perception. Perception that's clear in this case of collaborative AI is first to recognize the environment, where the robot has to do something. In our case, navigation means move around in the environment, recognize obstacles, recognize the path, identify objects, identify and track people, and also interpret the situation where the robot is at that moment. That is very important because depending on the situation, the robot has to do different, has to behave in a different way. And also we have that is called cooperative perception. And I show you here one example. There are several robots, 2 robots, and also infrastructure. Infrastructure in this case is cameras in the buildings. By the way, that is one part of our infrastructure, urban infrastructure in the UPC, in the campus north of UPC. And what you see in front of you, it is the Faculty of Computer Science. And okay, you can do cooperative perception through different elements, the robots, and also, for example, in this case, the camera of the infrastructures. And put together all this information is what we call cooperative environment perception. Okay. Also in communication. Communication, what means when in collaborative AI? That's clear. Dialogue in speech, text, visual, whatever. But also we have non-verbal dialogue. Non-verbal dialogues, you can see here on the right side, that in the robot, in the bottom part has a yellow line, then is detecting the person. And in this case, the motion of the person has some connection with the robot. The robot identifies the motion of the persons through this LiDAR information. And then there is with that, it creates some kind of non-verbal dialogue. But you can also see in the bottom part of you can see also when the robot and the human touch together, there is a physical connection. Also, there is implicit communication. That means if we are, for example, bringing something together, a table, and the person is pushing the table, and the robot is also trying to push, the robot is perceiving through the sensor, the 4 sensors, what the human is doing. And in this way, we have a dialogue, but in this case, it's implicit dialogue, instead to be not a typical speech or text or visual dialogue. And also in non-verbal dialogue, there is something additional. In the human relations, that is approximately, but that is more or less that. 40% is verbal dialogue, but 60% is non-verbal dialogue. It's the motion of the person, it's the motion of the face, is the gestures, there are other kind of information that is transmitted between humans. And that is something that is also very important when we do this kind of communication between, when we have to do communication between human and robots. Okay, decision-making. Decision-making has different elements. You can see here, reasoning, planning, that's a typical kind of decision-making. And from this planning and reasoning, we make the decision to do something, to move, to talk, to do whatever. But also we have intentionality. And you can see here in the part of the picture of the middle, you can see a person that is a giver and the other is the receiver. And the receiver takes a look what is the giver is doing, and in this case is giving some kind of bottle, and immediately the person sees the intentionality of the person in order to approach and to change and to move the hand to another position in order, in this case, to hand over the bottle. But also this agreement. When we do together with humans and machines or robots has to do an operation, has to agree in doing this operation. And this kind of agreements many times implies negotiation. If I have to do a robot and a person has to do a plan to look for something, for example, to look at an object in a house and we don't know what it is, both they will make their own plans, but they will decide where to go. And then they have to agree where the robot will go and when the person will go. In this case, what happens in our experiments, what we do actually, it is the robot tries to estimate what the human is going to do. And then the human, because we don't know exactly what is thinking the human, but we can make an estimation of their intentions, and from these intentions, then we will able to make a plan and then present this plan to the person and they agree what both will do. That is an example of what can be this part. But also there are interaction. There are social interaction. Social interaction means follow the social rules that the humans usually do. And also the humans with pets, there are some kind of social rules. Okay, but also there is physical interaction, contact. When there is contact between robots and humans, that implies this kind of interaction that can be by using the force sensor, the visual sensors, the tactile sensors, whatever we can do. And in general, human-robot interaction, whatever it is and whatever implies and which the behaviors that is are behind that, okay? From the point of view of the human, in order to know what the human is thinking or what is doing or what is trying to do in a specific task, there are some theories of mental models that look for that. And that has to be used in this kind of interaction, okay? Okay, let's go into what I'm going to explain in the next slides. It will be, we do experiments in real life experiments, that is in the Barcelona Robot Lab, that is this infrastructure that you can use if you come here to do experiments. And you can see on top left, the complete infrastructure. There is a 100 meter by 100 meter, 10,000 square meters, where we have cameras, we have computer, we have sensors, and then we do our experiment here with people, usually our students and staff people of the university that is inside of the university. And you can see here some picture of the UPC North Campus on the middle, and also south in the just besides our institute, we have a small area that also we do some experiments, and you will see videos of that doing with this kind of areas, experimental sections. Also, we have robots. I show you only TV and Davo. There are two robots, but actually we have a new one that is Ivo. But in other than you take, you see here, this has some sensor, GPS, stereo camera, tactile screen, microphone, and speakers. And also they have some sensor for navigate, that is this horizontal and vertical leader, and encoders, and that are used for localization, the location of themselves, and also for navigation. And that's clear, we have the computer running on site of this. Okay, let's going to start with navigation. Then we have developed quite several years ago. That is human-aware navigation. And, and you can see the idea. Okay, what we want is to navigate alone, the robot, or accompany some other people, or doing approaching or whatever. And in an environment, there are static objects, like you see walls and can be obstacles in the middle, but also there are other people that can be static or can be moving around. And can be also bicycles, and can be vehicles. And in some way, what we have to do is to first to have the map of the area that we were to do this kind of navigation, but also we have to, every time, in very short time, we have to detect what is the people that is moving and predict their motion, because our motion will be, we will have to take in account the motion of other people in order that the robot can navigate in a human-aware way. Human-aware way means that the robot is aware of the people and how they move, how they behave. And they change, the robot changes its navigation behavior depending on the other people. But always thinking that the robot has to reach the goal. Right? And then you can see here the human motion and also the robot navigation. The robot navigation, and I will explain how we do that, it makes finally the plan to move, taking account this, the static objects, and also the propagation of what the human, the people that is moving is going to be in each instant of time. Okay. Now, in order to do that, we use something that is called social force model. That was a work of Helbing in 1996. And from this, we have extended this social force model. You will see how we do, and I will explain in some details. Okay, let's start, but what we want to do. Say, what we're gonna take a look is the following. We wanna observe our environment of an environment where there are forces that are attractive forces and repulsive forces with respect to us. And we have to produce a force to move the robot. In this case, there is this Fn is the force that will, the resultant force in order to move the robot to our goal. And our goal is destination 1 or destination 2, okay? And this is what is called this, first what we will have is the steering force. The steering force is the attractive force that will then attract the robot to this goal. And this attractive force, in this case, is going to come to one destination to another destination. And we have some methods in order to decide which destination what the robot wants to go, okay? Now, the steering force is computed directly by the velocity of the robot and what we expect to be the velocity and the real velocity of the robot. And this multiplied by a coefficient, then finally this is a force. Okay, in our case, we consider that the mass of the robot is 1 and the mass of the person is 1. There is a simplification, that's clear. That is, it's like a kinematic way to focus this problem. But it's a way in order to facilitate the way to compute the forces. We can also include the dynamic forces and include the inertia, the Coriolis, and the gravity, and all this. But in this case, I will explain in a simplified, in a kinematic way, okay? Now, where we want to go is to find this force, and the F, there is the steering force that will be the F goal, that is the force that the goal attracts the robot. And that is our summation here in the upper part, okay? Now, we have interaction forces. Which are the interaction forces? All the rest of the forces that are repulsive forces with respect to the robot. I say one person that is approaching, is moving close toward the robot, it will imply that there is the produce an interaction, and the person will try to go away from this person. The same with respect to objects. The forces, these forces that you see here, this force, there is the force with respect to other person produced to this person, and also this is extended to objects and to, for example, robot to the a robot or whatever object is behind that could be static or dynamic. And you see that this is computed as an exponential with respect to the distance, and also we include, but it's not here, also the velocities in the case the motion of a person. Okay, that is the repulsive forces with respect to objects, and that repulsive forces with respect to robots. And finally, we get our final force, that is the force, then the resultant force, then we have, that is the summation between the positive part of the attractive and the negative with respect to the repulsive forces, okay? And finally, there is the force that will imply a velocity of motion of the robot to go to the desired, to reach the desired path. Okay, this is what you see here is this, when the robot do that, we estimate the motion of all the person, not over the distance, the usual distance of time, but with respect to all distances of time in an horizon. Usually we consider that this horizon is around 5 meters because the robot is moving around 0.8 meters per second, 0.6, 0.8 meters per second, and then we have an horizon of 5 meters that are several 7 or 8 seconds of motion of the robot. Okay. Now I'm gonna show you here how it works. This planning that is human-aware planning. Okay, and you see here the people state, the robot state, the dynamic constraints, the dynamic of the people, the dynamic of non-orthodynamic constraints. And in this case, I show this anticipative kinodynamic planning using RRT. You know that RRT is a very well-known path planner, a very fast path planner. And I use this because it's easy to understand each one of the elements that are here. Okay, now, one of the things that happens is we have to predict where is the situation after some time of the motion, not only of the robot, but also of all the rest of the object of the people that is surrounding the robot. And that is done using this extend function. Okay, yeah, I will explain a little more in detail later on. Also, we compute some cost to go function, then I will explain later on and more in detail because of all the potential paths that can be done, we will select the best one, the best that minimize this cost function. And finally, this find the nearest vertex. Okay, the extend function is the one that in this case you have on the top right, you have the robot, that is the XRT in this triangle blue. And there are two persons that are moving to different destinations, and they are going to cross the robot, and the robot has to compute what is the people going to be in each instant of time when it's moving, and then compute if they can follow this path or another, taking account not only their own motion, but also the motion of the other people. And you can see also that this motion of the other people has an uncertainty that is growing over the time. Because at the beginning, we know quite well what it is, but later on, we only do an estimation, and that we do is to propagate in the uncertainty, that is these circles that you see here, are increasing every time in the time, okay? Now, we do that, and you can see here the horizon. As I have told you, when we compute where the path has to be computed, we do a global computation from the position of the robot to the goal, but this, in order to compute everything with respect to the people that is moving or the objects that are around us, we have an horizon, that is this circle that you see here, and from the path, we select one point of the horizon that is this red point bigger here than you see. This is the point that the robot will go, and that will be the on goal, because in all our model, we need to know the goal, where the robot is going to be, and the goal, where the person is going to go, or any of the objects are going to move. Okay. Now, you can see here all this environment in simulation. Actually, this simulator, the complete simulator, we have available, and the people that wants to work with this can use this kind of simulator. And you see here the different elements. This is the blue is the goal. This is the lines. The random path is the path that the robot is always planning at each interval of time. That usually is 100 milliseconds, 200 milliseconds, sometimes more, depending on the number of objects that we have. And you see here the other object that have this number 10, number 12, whatever. That is where the people will be in the future position. Okay. Now, this applied to our robot, and you see here this navigation in real environment, that is the UPC infrastructure, and you see people here moving. You will see later on more in detail that part, and then you can see some of our experiments where the people is going from in front of the robot, and the robot reduce the velocity and change the trajectory in order to overcome the people and also all the obstacles, but always taking account that has to go to the final goal. That is the goal that the robot has to go. Okay, you can see on the left bottom part what is the horizon, what is the final decision of the robot, where it has to go. That is the path, the final path. But the rest are not like vertices. These vortices are nothing but the estimation of where the people will be in the future, and this path has to go in between the valleys, in between these vortices, and the best one will be the path that finally will be selected. Okay, and you can see many of these motions here. And you can see here one example that is very interesting. The robot is moving. These people doesn't know at all. The people are playing with a ball doesn't know at all that the robot is moving around it. And actually, they don't do. They continue playing, and the robot modifies completely the trajectory in order to not avoid them and continue. And that is what we call human aware. Okay. Now let's go now to. We have seen now with respect to one robot moving. Doing alone when there are people. But now we're gonna do the accompany. The robot is gonna accompany someone, and has to go from the bottom position to the upper position, where is the goal. And you can see that there are 3 different plans to go from this position to the final goal. But in each one of the plans, there is an accompany side by side. You see that, for example, the middle of the path implies that the robot and the person in the beginning are side by side, but then, in this case, the robot go ahead because there is a narrow place that only the person or the robot alone can go. And then after that, when past the narrow part, they begin again side by side. And you can see also similar of the other 2. Okay, we do very similar, but you will see here on the right, you can see different parameters that have to be taken in account. That is, when you do side by side, you have to take in account the distance between the person, the angle. It is actually side by side, or the person is a little in front or behind the robot. And also with respect to the obstacle, the distance with respect to the obstacles, because all this has to be taken into account every time that the robot is moving. Okay, we use the social force model anyway to do this, and you have here the FR is the resultant to propagate, But you can see first the attractive force until the dynamic goal. That is the same that we saw before. That is the attractive with respect to the goal. But you have here another one that is the attractive force to maintain the formation. The formation is the side-by-side formation. And that is, in this case, there are two forces, two attractive forces. One is to go to the goal, and another is to maintain the formation. And then the rest is the repulsive force with respect to other people and other obstacles, okay? Now, here, what you see with respect to a collaborative AI focus? Well, actually, we have perception. We are detecting the environment. We are the obstacles, the people. We detect the company. We are always detecting the person where it is. It is just side by side, with a little more in front or behind. We have a communication between the human and the robot. Is this communication, it is doing, one is implicit and another is explicit. Explicit is verbal. The robot can tell something to the person and tell, well, please come closer, or in this case. Or implicit, it means that because the robot is detecting always the person, immediately, if it goes far away from, if the person is going far away from the robot then approaches to the person. And then the person perceives that kind of, then the robot is closer to it. And there's a communication. Immediately, the person understands that. We also have the intentionality. There are different kinds of intentionality. One is with respect to the person, that is a company. In this case, always the person is who has who is really giving the path in some way. It's the telling, not telling, but by their own motion, is telling to the robot where where it wants to go. But that is one part of the intention. But there is another intention with respect to the rest of the people that is moving around. Then we know by predicting where they will be in the future, what is the intention of the person. We have also adaptation. Every time that we are doing this motion, the robot is adapting to the person in order to maintain the formation and adapting to the environment to try to avoid obstacles and avoid motion, in this case, motion of the pedestrian, but also the motion of any of the objects. And there is an interaction. In this case, there is not interaction with a company of two persons. You will see that there is an interaction directly. And there is an agreement between the robot and the human, because there is an implicit agreement. The robot will try always to maintain the side-by-side, but the person also will try to maintain some far away from the robot. And this is a kind of agreement between them. And the decision-making. The decision-making, this is in this case, is the planning and reasoning, and the robot tries to maintain, to follow the path, to maintain the formation between them, and to stop if our object is coming closer to it, or this kind of decision-making, okay? Now, you can see here, well, some kind of, the robot is moving around. In this case, it is more, well, the robot is trying to face the person. That it was one of the first started motions. And here there is a company with another person where there are obstacles in the middle. And you can see the person is moving. The robot is, in this case, is going behind. And okay, this is, you have seen this through a combination, linear combination of forces, attractive and repulsive forces, in order to do to find what is the motion of the robot. But also we have done that with non-linear social force model, in this case with a neural net. And in this case, I will not explain, but I will only tell you that we use a neural net where the inputs of the forces from the environment, from the object, the attractive forces, from the estimation of the other person. Here you have the human estimation on the bottom part, that is also give an input here. And then with these two, we decide what are the accelerations of the robot and every time. And because we have considered that the mass is 1, the acceleration is directly the force that is going to be applied to the robot, okay? Okay, now, when we do a company of 2 persons, it's a little more complex because we have to try to maintain the formation of 2 persons and the robot. Meanwhile, things happen around. That is, the other people is moving, and we have the static, etc. And then, in this case, again, we use the ATP, the anticipative kinodynamic planner, to look the best path. But also, we are doing the force of the robot in order to maintain the formation, in this case, the formation of 2 persons. Okay, we have the force until group destination, and we have also all the repulsive forces with respect to the people. And again, we have the same elements, but now we have to accompany 2 persons every time. That is much more complex, okay? Now, for example, in this case, we have included an additional element in order that the 2 persons can maintain the robot accompany these 2 persons. We use a game in order to engage the people and the robot at the same time. That is a game, very child game. Then that is the TV says the name of the animal begins with a letter, and then the 2 persons try to discover which is the animal, and with that we try to maintain that they both continue together with the robot. Okay, that is for our experiment has been a good way to see what happens. Okay, now I'm going to explain a little more in detail, not too much in detail, but a little more in detail, what are the forces that are involved in this case. And you can see here there is 2 kinds of formations when there is 1 robot in 2 persons. One is robot is on the right and the 2 persons on the left, or robot is in the middle. Okay. And now I'm going to go a little more in detail in order to you understand what happens here. Then it's a little more complex. When the group, that is the person with the robot with the 2 persons has to go to this destination, that the end goal. Actually, this has to be separated in different destinations. Why? Because there is the destination of the robot and the destination of each one of the persons. You remember that our method is always based in we know what is the destination, our local destination, and we compute the forces to go to, the attractive forces, and each one of these goals will be the attractive forces for the robot and each one of the persons, and then and there are the rest of the repulsive forces. Okay. Now we have here, now this is the force of the group destination, and this is divided in these forces that you can see here in PC1 and PC2, and there is one is the PC1 is with respect to the person on the left, and the PC2 is with respect to the person on the right, and finally the robot has to take in account the destination of the person, because the robot will try to follow the behavior of the person in order to maintain the formation. Okay. Now, by another, we have the repulsive forces that are done or the respect to the different elements that are here, and also the other objects that are repulsive forces of other forces, and the resultant force will be F. Sorry, will be F. That will be the resultant forces. Now, with that, because AKP creates different trajectories, different paths, we have to select the best one. How we select this best path? We use for that a cost different. We evaluate some costs with respect to some criteria. One is the cost to reach the goal. Another is the cost to orientation. Another is the cost of control the robot. And another is the cost of the pedestrian and the cost of the obstacles. And all these costs, and also there is the cost of companion. And all these costs, we try to minimize. We were trying to find the minimum of this cost, and the path that has the minimum of this cost will be the one that will be selected as the path to follow. Okay. Now, also we have some metrics And this metrics is what, in order to maintain the robot in a specific area, we define some areas where the robot and the person has to be, and what is the situation. On the left, you see in the case of the robot is in lateral, is in one extreme position, and in the other, the robot is in the middle. And we define some parameters in order to do these metrics. And okay, you can see here now one of these. This is one person. Here you will see 1 and 2 persons. The robot is trying to maintain. Now it comes another person, also wants to take a picture. Okay, now the robot is accompanying 2 persons. He's a little behind, you see, then is a form, then is V form. Then it's typically what happens when we do this kind of accompany. Sometimes they're completely aligned. We have compared with completely aligned with this V formation that is actually the robot is behind them. And usually there's a typical way that the humans do. Now here you have another of the positions. And you see all these experiments is in a real environment and also with other people moving around. The robot is not going fast. It's in these cases we always go very slow, 0.6 around that. Sometimes we can go a little higher, but that makes them sometimes the robot is behind.
Alberto, we can't hear you. Please
Okay,
open.
now I'm sorry, but
Okay.
I tell you that this I will try again to restart. Okay.
Okay, we can see your presentation now.
Okay. I tell you, and I don't know the reason why, but it has happened now. Okay, now this is approaching. There is another technique is how to approach people, and this is you can see here on the middle part. There is we define some points where the robot has to approach to a person. And in this case, we have to know what is the direction of the person in order that the robot goes in front of the person and can be just in front of the person or a little on the left or a little on the right. And also we use the social force model for doing that. But also we have doing the path is we use a kind of G2 is like an spline, a different kind of spline that we use to do this G2 spline path. And you can see here some examples of this. Okay, there is approaching one person. You see some examples of approaching. It is important because if the robot is not going to be just in front of the person, then what happens is then the person thinks that the robot is not interested in something that is not related with them, and they don't engage with them. Okay, and you can see here several examples of this moving and approaching to the persons. Okay. Okay, now again, in here you have all the elements that I have been talking about: perception, communication, intentionality, adaptation, interaction, agreement, and finally decision making with all the information in order that the robot can move. Okay. Okay. Now, what we have seen up to now, it is a company. But now, another of typical things that now is very useful is, and it's very typical in the daily tasks, or the part of engaged people. And we make some experiments of engaging people with a robot. And we do this experiment also in this campus north in the infrastructure, the Terranet infrastructure. And you can see in this graphic, the part of the initialization, the robot looks for a person, in this case using the leader, or can also use, in this case was using only the leader, but also can use the camera, the top cameras, and the persons, well, is around that. When the robot finds a person, start to talk with them, say, approach, please, I want to talk with you, and something like that. And then if the person finally wants to do engage with the robot, then stop in front of it and start a conversation. That is the part, the assistance process. No, the engagement is created, and then the human assistance starts, and the robot makes some questions. The person answers that, and there is an interaction between them. And when it's finished, the experiment, in this case, this experiment, the robot say goodbye and then finish the part. Okay. Now, and you can see here that there are many elements. Here, there is perception system, the people detector, the track target, the human face detector, robot motion with human-robot interaction, plan trajectory to approach the person, express emotions, ask doubt, express emotions, plan trajectory. The robot has to look the people, find the participant, approach the person, create engagement, experiment description, learning stage, etc. No? Then there is a very complete and many different elements that are incorporated in this kind of experiments, not only that are the part of the collaborative AI elements that I showed you before. Okay. Now, also, finally, I'm going to explain another example of robot navigation together with people, but in this case, the robot has to search and follow people. And that is, you can see here, the experiment. We have, in this case, the beginning is only one robot, that is Davo, then it's moving, and it's trying to find a person. Then the person has this label you see on the top of it. And the robot, what it does is first detecting people, and then try to find with the camera what is this label that you see here that brings the person, and always is moving around. But you see these people is trying to avoid, and the robot it sees the label, and because they are joined together, and then the robot has to do different things in order to find the person. No? Okay, once the robot finds the person, then the people go away. Okay, on the right side you can see the beliefs. When there is red is higher belief, when it's white is lower belief. Okay, and the belief, and there is always creating a belief map of what are the different states. Okay, now you can see here the case of two robots, not one robot, but also in this case it's two robots, then or in a bigger space, there is something like 60 by 60 meters, and the robot has to find a person that has a label. You see on the left the beliefs, the belief maps, and when this red is, the robot has found the person. And in this case, both robots has to do exploration, and then when they find the person, they follow the person. Okay, and that is a kind again of collaborative AI between human and robots. And in this case, when both robots do in the start, and they do by themselves, but then they collaborate. How they collaborate, you can see in here in this graphic. The robots share information of what they see, what they perceive. In this case, they use not only the LiDAR, but also the stereo camera in order, in this case, it is not a stereo camera. There are 5 cameras at the same time on the top of the robot, and they look 360 degrees. And the LiDAR also is 360 degrees, and they can more or less. And they whatever they observe, they send this information to all the robot participants. But when they take a decision, they also, the belief update, the belief that is where they think the person it is, also they share between them. And the decision they share between them. And in this case, they are able to find and look a person than try to find the person that has the label and follow it. Okay. Okay. That is all that I wanted to explain. And now I am open to questions. Whatever do you think you want? Okay. Okay. Do you have any question?
Alberto?
Sí.
Yes, we have a question. Can I read it for you? Can you see the chat? Or?
Yes, just a moment. Okay, I see now. I am able to see the chat now. Okay.
By Mateus Sanchez.
Yes, Mateo Sanchez is, can the human-aware navigation framework be used for mapless navigation? It is subject to local minimal. Okay, let me see. We can find a local minimal. Yes, we can. We have that. That happens. However, what we do is, if after sometimes we realize that we don't find for example, the person, or we find a place that is stuck us, we change the motion and the direction, the orientation, and we modify it, then overcome this local minima using some additional information in order to minimize the problem. Now, also with how the people is tracking, doing. Okay, what we do, we use sometimes we have used Kalman filter. But basically now what we use is particle filters. Most because we realize, okay, you know that in the Kalman filter, what you have to have is a very good estimator. Okay, in this case, it's okay. I mean, you have a very good estimator of the robot, and also very good estimation also of the people, more or less. But anyway, in order to overcome some situation, then we don't know where the person it is, the particle filter gives us additional information, because when we are looking, exploring some part, we are following someone that has disappeared because these are obstacles in the middle, then particle filters allow us to estimate a little further than Kalman filter. And for this reason, we use particle filters. And then Juan Luis Rosendo asks, in the experiment you show, how is one person to follow discriminate from another? Because, okay, with the LiDAR, we detect all the people, all the person that are moving and all the static person. But what we do, we have also the cameras on the top of the head. We have 5 cameras, and these cameras are detecting the people and are also detecting the label that the person has. And then in this case, we can discriminate which is the person that we want to follow using this label. We have expanded that now using a neural network, and then we were able also to track quite well people with the neural network, and also to identify the person that we want to follow. And it is quite good. And now we are making an experiment together, not with the label, but with the neural network. Okay. Okay, there's more questions. I don't know, Juan Luis, if I answered you.
Okay, there is something else. Yes, Kenny Shell. I'm sorry to pronounce your name. Do you have a strategy for the robot's behavior in very crowded situation? Okay, well, what the experiment that you have seen is more or less all the experiment that we have done up to now. When it's very, very crowded, still we have not done this kind of experiment. There is a problem behind it, is the localization of the robot. Because, okay, GPS, you know, that is very bad for localization, for accurate localization. Although we can use differential GPS, although that in these urban surroundings, the GPS still is quite bad for localization. And then what we do for precise localization is mapping the readings from the leader with respect to the map. And then we can do a very accurate localization. But when there are many, many people around the robot, we cannot localize the robot. And then we have a problem. Okay, we can localize. Yes, we can continue localize because we use odometry. Odometry plus we fuse odometry plus the GPS plus the information from the readings from the environment. But when there is very, very crowded, there is a problem anyway. And Juan Luis Rosendo says, in your opinion, what are the main open research problems on this topic? Okay, there are many topics here behind it. Okay, because I show you basically all the part of the navigation part. However, the behavior of the people, it changed a lot of, and we have to know the preference of the people. I say there are some people that likes that to be in front of the robot, other people likes to be behind, other people likes when there are someone approaching, they will immediately go and go. Then the robot has to know that, and it has to learn what is the behavior of the people. Also, the people that surrounds. There are some people that like very much to go near the robot. There are other people that are afraid of the robot. And also this preference has to be learned. It has to be known what it is. But this is aspect with respect to the human. But the robot itself also has to be developed has to be improved in different ways. In the collaborative part, for example, the plans, we have to do the plan of the robot and the plan of the person, okay? But then we have to have a shared plan. We have different ways to do shared plans. But then the robot, because doesn't know what is in the mind of the person, has to estimate what is going to be the behavior of the person. And then this is not easy at all, because, okay, there are some kind of a standard way to do the things together, or at a specific task. But there are some people that are very crazy ones, and they do in a different, very, very different way. And then the robot has to be aware of that, and has to know what are these strange situations and how to overcome them. There is something that has to be investigated. Also, something like what is called situational assessment. When the robot finds a person or tries to approach to a person, has to assess the situation every time in order to know what is the best decision to take. And to assess this, to make this situation assessment is quite complex, because depends on many, many different kind of issues, not only perception, but also the attitude or the behavior of the person. And then there is something that has to be learned in order to be included in the system. Okay. What else? Okay, I think now is 10 o'clock. There is a very perfect fit of with respect to the talk. Then you can. I hope you enjoyed the other talks. And if you have,
you have a last question by Mark Auledas.
Oh yeah, I'm sorry. Yes. Could you explain if you have used any reinforcement learning methods for human-aware navigation? Okay, we are using reinforcement learning at present. I have one student dedicated to that. We are using now reinforcement learning for prediction and also reinforcement learning for planning. and we are doing very good results now we have with this kind of learning. We use both reinforcement learning and also typical neural net learning with different kind of methods. I say typical, what is that? Well, different kind of architectures, also with GANs. And this is, this kind of results will be published very soon, because now we are making these experiments, and we will do this. We will have this experiment very soon available. Okay. Okay, I think there is no. Okay, good. Good. I hope you have enjoyed. I don't know if I have bothered you too much. And now continue, because it is we have a very good, very interesting presentation. Continue this one. And if you have any question, please send to us. And please, if there is people here in the audience that is interested to do research with us in this environment and using our resources, making your own that's your own algorithms, send an email, and then we will explain you how to apply to Terrinet project, the European project, and you will able to do your experiment with, we will pay you the fly and also the stay here, and also the resources to be and assisted and supported by our people. Okay, good. Thank you, and continue. I think you will enjoy all the rest of the conference.
Thank you, Alberto.
Okay. Bye-bye.